Welcome, honors students, and happy Monday to you. Today we're going to finish up 15.2. We've been talking about aqueous systems and specifically homogeneous aqueous systems, and that's what we called solutions. So we looked in the last virtual lesson, we talked about solvent and solute, and we learned that a solute goes into the solvent to form a solution. So we looked at electrolytes and weak electrolytes, strong electrolytes, and non-electrolytes. So hopefully you watched that virtual lesson and took some notes. So today we're going to begin the process of talking about hydrates. And what is a hydrate? You're actually familiar with it because we worked in several labs with hydrates. Particularly, we looked at copper 2 sulfate. So we had CuSO4, and it was actually copper 2 sulfate pentahydrate, which is, and this is how you'd write it with this little dot, and then it would be 5H2O. So that penta is 5 water. So that means in this particular compound, this copper 2 sulfate, there were 5 molecules of water in the crystal structure. And that's what a hydrate is. It is a compound that has water molecules formed inside of their structure. So why do hydrates lose water easily, lose or regain the water easily? So we did a lab a little bit earlier in the year where you actually had some copper 2 sulfate pentahydrate in a test tube. And it was this nice sky blue color. And you laid it on a hot plate. So here you had this test tube. And inside you had this fine powder right here. And then you have the hot plate right here. And when you laid it on that hot plate, you noticed that some steam came out of the test tube, and you saw water droplets form on the side of that test tube. And after about 15 to 20 seconds, you noticed it was no longer that sky blue. It was this white color. And that was the activity where we were actually making that hydrate lose the water. And then once it had that white color, then we added back some water, some distilled water from the water bottle. And hopefully you remember that. And it turned blue right away because it reformed the bonds. And that's what we're going to be talking about here with hydrates. So the water contained in a crystal is called water of hydration or water of crystallization. And we just sum all those terms up with hydrate. A compound that contains water of hydration is called a hydrate. So please make sure you place this in your notes. That's an important term. When you talk about a hydrate, it is a compound that has water in its structure. So, key concept, the forces holding the water molecule are not very strong. That's why when we place that copper sulfate on that hot plate, it turned white. It lost the water. So the water is easily lost and regained, and that's really important here. So a substance that is anhydrous, this is another key term. Please place this in your notes. What is anhydrous? Anhydrous is a compound that does not have water in its structure. A lot of organic compounds are anhydrous, and it will say right on the label, anhydrous. So you could have anhydrous copper sulfate. That means that it does not have that 5 water molecules. So that's what anhydrous means. Please get that in your notes. So here is just a little demo. We didn't use the Bunsen burner. We actually used a hot plate, if you remember. But this is, once again, I showed you how you write it. Here you have copper sulfate pentahydrate. And when you heat it, you notice that rich sky blue color is gone. They don't show the upper part of this test tube, but if you were to look up this way on it, you would have seen steam coming out and some water droplets forming on the sides. That is how the water is lost. It just evaporates. It's a very weak bond that's holding it together. And once it's lost, it's white, and it's actually now anhydrous copper 2 sulfate. So you could also look at, for example, here we have some test strips in Cobalt 2 chloride, and this blue right here is dried, so it's anhydrous. But if you take it and you expose it to the air around, there's moisture all around us. It turns pink right away because now it is picking up the water out of the air that's around us, and it becomes Cobalt 2 chloride hexahydrate. Here is a bunch of names. You don't have to worry about memorizing them. It's not important that you know all these. Just understanding that these are hydrates, meaning that they have a specific amount of water in their bonds. So you could actually determine the percent composition of water. And we're going to look at an example a little bit later, but this formula right here is very similar to percent composition. So remember earlier in the year when we were looking at, say, let's say here, calcium. We're going to look at calcium chloride, CaCl2, and you wanted to know what is the percent by mass of calcium chloride. So what you do is you take the total mass divided by the mass of the calcium, and you'd be able to calculate the percent composition of calcium in calcium chloride. So same principle works with this. When you talk about determining what percent by mass of hydrate is water, you take the mass of the water divided by the mass of the total hydrate, including the water that was in it, multiplied by 100, and that's your percent by mass. We'll look at that calculation a little bit. So now let's talk about some terms. These are some real important terms, so please make sure you get these in your notes and be able to differentiate between them. Efflorescent hydrates. The water molecules in hydrates are held by weak forces, so hydrates often have an appreciable vapor pressure. So that means that the vapor pressure, it can escape. The water can escape. If a hydrate has a vapor pressure that's high, meaning that it's going to escape fast, it's going to escape very quickly into the atmosphere. So the hydrate will lose its water. It's called effloresce. So this is a term right here you should place in your notes. Effloresce means that this particular type of a compound that has the hydrate in it, the water will escape quickly. So if you dump it out of the container that it's in, it will become anhydrous pretty quick because it has a high vapor pressure, and the water will escape out of the bonds and go into the atmosphere through just evaporation through the vapor pressure. So that's called effloresce. So the hydrate will lose its water of hydration, and that's called effloresce. So please have that term in your notes. The next term we have is hygroscopic hydrates. Hygroscopic. These have low vapor pressure, which means they're not going to lose their water that's in their crystal structure into the atmosphere. Their vapor pressure is low, so these actually will accept water from the environment, from the air around us. It'll accept the water from the moisture that's in the air. It'll accept it. Those are called hygroscopic. Hygroscopic. So these hydrates and other compounds that remove moisture from the air are hygroscopic. Hygroscopic. So that's another term. So we have effloresce, and now we have hygroscopic. Effloresce will lose its water of hydration into the air, whereas hygroscopic will not. It will actually accept water from the atmosphere around it into its structure. So let's talk a little bit more about hygroscopic hydrates. So talk about calcium chloride monohydrate. Spontaneously absorbs 1 molecule of water from the air around it. So it's called desiccant. Another term, please get into your note. A desiccant is a substance used to absorb moisture from the air and create a drier atmosphere. Desiccant is like Damp X that you find in the store. You buy that stuff. It's usually put in closets and things to keep moisture out. That's a desiccant. It will accept water vapor from the air around it to dry the atmosphere in that room. So that is called desiccant. So please get that into your notes. Real important term. So let's do a calculation quick here. First off, let's look at them do one, and then we'll do one as well. So here we have some washing soda, sodium carbonate, Na2CO3. Carbonate is an polyatomic ion, if you remember. And in this one here, it has decahydrate, means it has 10 water molecules. So they want to know here the mass, the percent by mass of the water in it. So first off, you got to calculate the mass of the water. So you take the H2O 16, 17, 18, and you multiply by the 10. So basically 180 grams is the mass of water in one of these molecules. So now you take the mass of the sodium carbonate plus that. So that's what they're doing here. They have their 2 sodiums right here. They have their carbon, they have their 3 oxygen, and then they add the 10 waters is right here. They add it all together and they get 286 grams. So now they take the water divided by that, and let's look at what they're doing. So the mass of the water divided the total mass of the hydrate. So 180 divided by 286 times 100, and 4 sig figs, 62.94%. That's the percent of water in that compound. All right, so let's get another term down here. So deliquescent compounds. So deliquescent will actually accept so much moisture from the atmosphere around it that it will actually become a solution. So we have another term here, deliquescent. We actually have several of these in the lab, and I have to keep them inside of a plastic bag. So we have the bottle, put the little bottle like that, and I have to make sure that that lid is very tight, and then inside I put it in a bag, and then I tie the top of that bag. Take all the air out and then tie the bag, and that in an effort to try and keep it from absorbing water from the air around. Deliquescent means that it will remove so much water from the air around it that it will actually form a solution. You remember what a solution is? It's a liquid. So that's pulling a lot of moisture out of the air. So deliquescent is another term for us. And here is example of deliquescent, sodium hydroxide. So here are these pellets. It's in a container that's inside of a airtight bag, and you put it in a bowl or plate or petri dish or beaker or something of that nature. And within a short amount of time, you're talking within hours, you could come back and now you have a solution. So it's that much moisture out of the air. So deliquescents are important. They have their use to dry out the air in different environments, but this is an example of deliquescent. All right, so let's look at this checkpoint here. So calculate the percent by mass of water in Epsom salt. So magnesium sulfate heptahydrate. So here is our formula. So we're going to do this calculation here together quick, and then we'll look at it. You might want to pause the video and try it yourself, and then come back on and do it. All right, so let's look at this. So magnesium, we have 24.31, so 24.31. We have sulfur. Sulfur is 32.06, and oxygen is 16.00, and that's times 4 because there are 4 of them right here. And then we have the water times 7. So we're going to do the water over here. 7 times, if we already had said that, 16, 17, 18, 18.02. We're going to be real specific on this. All right, so let's get our calculator. So we're going to have to add that over here too, because that's in the total compound. So let's get our water and then get our total compound mass. So if we go 18.02 times 7, keeping at the 4 sig figs, this is 126.1 grams. So let me come over here and go 16 times 4. So I have here 64.00. Here I have 126.1. So let me add all these up here. So I have 24.31 plus 32.06 plus 64 plus 126.1. So I have to round because this is addition. You can't have more significant places than the least number of significant places. And it's in the 10th position here. So I have 246.5 grams. So now I'm going to take the hydrate and then divide it by the total mass of the hydrate. So I have 126.1 divided by 246.5, and I'm going to multiply that by 100. So let's calculate this out real quick. 126.1 divided by 246.5, and we're going to multiply that by 100. So keeping at 4 sig figs here, I have 51.16% water, and that is the answer. Should be fairly close. I don't know how many decimal places they carried it out to. And we have just a little bit more precise, 51.16, and they have 51.14. But the same process they went through. I rounded mine a little bit more than they did, but we have the same answer. So roughly 51% water based on percent composition. All right, ladies and gentlemen, that is it on 15.2. So tomorrow I will have another virtual lesson for us, 15.3. So let's go through here the key concepts. We talked about solutions. We talked about ionic compounds and electrolytes. We talked about forces holding the water, the hydrates together. We talked about calculating percent by mass of the water. We talked about aqueous solution, solvent, solute, solvation is the splitting apart of an ionic compound into ions. Electrolyte, non-electrolyte, strong and weak electrolytes. Water of hydration, a hydrate. We talked about anhydrous, lacking water. Effloresce loses the water quickly into the environment. Hygroscopic removes moisture from the air. Desiccant is used as drying agents because it pulls from specific sections that you might place it into. That's a desiccant. And deliquescent actually removes so much moisture from the air that it actually forms a solution. So those are the key terms, and that is it, ladies and gentlemen. So 15.2 is complete. So thank you for watching this video. Enjoy the day. Go in peace.